For example, the roundish atoms with hooks, shown in the animation, have a bitter taste and they are sticky. Today, we know that this naive atomic model is not correct. He described atoms as indivisible, tiny spheres. Although it later turned out that atoms are not indivisible, he had correctly assumed their existence.
In several experiments, he concluded that electrons can be extracted from the atoms of any element, and that thus all atoms contain electrons.
The outcome of his experiments is only possible if the vast majority of the weight of the gold atoms is condensed in a rather small space. However, the general experience is that atoms do not collapse. This atomic model is the best way to reflect reality according to our current knowledge of the structure and operation of the universe. According to Democritus and his master, Leucippus, matter is made up of tiny indivisible particles called atoms. According to their model, atoms exist eternally. They are neither destroyed nor produced. They can be different in size and shape, and they might be connected through small hooks. The peculiarities of atoms define the characteristics of different materials. For example, the roundish atoms with hooks, shown in the animation, have a bitter taste and they are sticky. Sweet materials are small and round. Therefore, they are able to infiltrate different materials, changing their taste. Today, we know that this naive atomic model is not correct. However, this theory is important in the history of science because it marked the birth, in the 4th to 5th centuries BC, of the notion of the non-continuous, quantized nature of matter. According to English scientist John Dalton, compounds are made of different combinations of atoms. He described atoms as indivisible, tiny spheres. Dalton's model was essentially an improved version of Democritus's atomic theory. According to Dalton, the consistency of materials depends on the distance between atoms. Although it later turned out that atoms are not indivisible, he had correctly assumed their existence.
By the end of the 19th century, it had become clear that the theory of the atom's indivisibility could not be maintained any longer. At the turn of the century, English physicist Joseph John Thomson noticed that cathode rays are made up of negatively charged particles, and with this, he demonstrated the existence of electrons. In several experiments, he concluded that electrons can be extracted from the atoms of any element, and that thus all atoms contain electrons. As atoms are electrically neutral, he assumed that the negatively charged electrons are embedded in a positively charged substance. Thomson referred to this as the plum pudding model because it reminded him of plums embedded in a pudding.
In Ernest Rutherford's experiments, gold foil was bombarded with alpha particles, that is, by helium nuclei. The majority of alpha particles simply passed through the foil, while a few of them changed their direction while passing through, and some of them were reflected from the foil. If the Thomson atomic model had been correct, all the alpha particles would have slowed down, but would have passed through the metal without any change of direction. The outcome of his experiments is only possible if the vast majority of the weight of the gold atoms is condensed in a rather small space. Based on his results, Rutherford developed and published his atomic model in 1911, in which the electrons circulate around the positively charged nucleus. The diameter of the nucleus is about 1/10,000th of the atom's diameter. The development of a new model became necessary because, according to some calculations, the electrons circulating around the nucleus in the Rutherford model should be emitting energy continuously, causing the electrons to slow down and spiral into the nucleus. However, the general experience is that atoms do not collapse. Thus, Rutherford's atomic model had to be modified. The problem was solved by Danish physicist Niels Bohr in 1913 with the following assumption: electrons can only circulate around the nucleus in circular orbits. Therefore, electrons cannot spiral into the nucleus. They can jump from one orbit to another. When it absorbs energy in the form of a photon, the electron is stimulated and enters a higher energy orbit further from the nucleus. The electron may enter a lower energy orbit through the emission of energy. As the electron can only absorb or emit the photon with the energy necessary for the jump, the emission and absorption spectra of atoms are not continuous. This matches experimental results with hydrogen atoms. Sommerfeld updated Bohr's atomic model and published his theory in 1920, which is also called the Bohr-Sommerfeld model. In this atomic model, the electrons can only circulate around the nucleus on certain orbits as well, but the orbits may also be elliptical. The Heisenberg-Schrödinger model is also called the quantum mechanical model of the atom. According to quantum mechanics, particles cannot be described as globules with exact locations. It is more realistic to depict the atom's electron shell as an electron cloud. We are somewhat likely to find the electron at particular points in the electron cloud. There are atomic orbitals in the atom, and within the orbitals there are s, p, d, and f subshells with specific shapes. This atomic model is the best way to reflect reality according to our current knowledge of the structure and operation of the universe.
Thank you for watching our exploration into the development of the atomic model. We hope you enjoyed uncovering the revolutionary discoveries that have shaped our understanding of the universe. If you found this video insightful or inspiring, please give it a thumbs up and share it with others who might enjoy or benefit from it. We'd love to hear your thoughts. Drop a comment below to share your feedback or ask any questions. For more engaging educational content, don't forget to hit the subscribe button and turn on the notification bell so you never miss out on our latest videos. Follow 3D Learning Lab on social media to connect with a community that values knowledge and innovation. Your support helps us continue creating high-quality learning experiences. Together, let's inspire the next generation of thinkers. Thank you for being part of our mission to make education exciting and accessible for everyone. See you in the next video.